Okay, good afternoon to everyone of my dear students. Yeah, your future doctors. So last class we discussed some concepts in chemical bonding, right? How to calculate formal charge. Okay. And then Lewis charge structure, how to write this all. Next now today we are going to do about bond polarity and dipole moment. So polarity of a covalent bond. Polarity of a covalent bond. The covalent bond is polar if it is formed between two different atoms. Then the polarity of covalent bond is expressed in terms of dipole moment. Dipole moment. So what is a dipole moment? For example, HCl is there. So it forms one covalent bond. But chlorine is more electronegative. It can attract the shared electron towards it. Because of that, it develops partial negative charge. Hydrogen gets partial positive charge, right? So two poles are developed. It is a dipolar molecule. It is a polar molecule, and it is a polar molecule. It is a dipolar molecule. Two poles are there. Now, here, because of this, the charge of any one of the pole and the distance of separation between the two poles is responsible for to find out the momentum of the dipole. This is called dipole moment. So dipole moment is denoted by mu. Mu is equal to charge on one pole, okay, into distance of separation of the two atoms or distance between the two poles. That is called dipole moment. So it is different as we have to multiply. That is the product of charge of an atom, any atom, and the distance of separation of the two atoms. That is called dipole moment. So dipole moment is measured by SI units divide units. It is capital D, not small d. It is capital D symbol, right? Okay. So one divide. So one divide is equal to how much? One divide is equal to 3.335 into 10 power minus 30 coulomb into meters. Coulomb into meters, right? Next, the dipole moment of covalent molecules is similar? No, it is different in different covalent molecules. Now, how can you find the dipole moment? That is the dipole moment of different covalent molecules. Different covalent molecules. For example, beryllium chloride, BeCl2. Here, central atom is beryllium and is bonded with two chlorine atoms. So, chlorine is more electronegative. That's why the bonded electron pair, that is the electron cloud, moves more towards it. The momentum of bond is towards the chlorine atom. So, this is the tail end or towards the partial positive, and the arrow mark towards the partial negative. So, this is the dipole momentum of this bond dipole is some x value. And here, the dipole moves towards the chlorine atom. So, the dipole momentum of this is some y value. So, x is equal to y. That means the magnitude of dipole momentum of both x and y is equal, but opposite in direction, right? So, both the dipoles are equal and opposite, right? That's why the dipole momentum of x is cancelled with the dipole momentum of y because both are equal. The magnitude of dipole moments are equal, but opposite direction operated. That's why both are cancelled with each other. The net dipole momentum is 0, right? Next one. Take it for example, carbon dioxide molecule. In carbon dioxide, in the carbon and oxygen double bond is present. Here, oxygen is more electronegative. That's why the electron cloud moves towards the oxygen. So the dipole moment of this is some x, and here also towards the oxygen, the dipole moment of this one is some y. Then x is equal to y. Both are equal, but operated in opposite direction. That's why the net both are equal strength. But bond dipoles of both are equal strength and opposite in direction. That's why both are cancelling each other. The net dipole moment is 0. Right. The same way, taking for example carbon tetrachloride. So here the second atom is carbon and it is bonded with 4 chlorine atoms. 4 chlorine atoms. Right. So here the carbon and chlorine is more electronegative. That's why the electron cloud is move more towards the chlorine. So bond dipole is moved towards the chlorine, and also towards the chlorine, and also towards the chlorine, and here also towards the chlorine. Right. So this is the bond. The dipole momentum of this is bond thing is A, this is B, this is C, and this is D. Right. Then the net dipole moment is equal to this A plus B plus C. So these are all in the same direction, but this one is in opposite direction. That's why this is minus B, right? The sum of all these three is x, and this is y. So there is both are equal, right? So that's why the sum of all these three is absolutely equal to that of B. That's why both are cancelling each other. The net dipole moment is 0. That is CCl4. Here 3. What is the dipole moment? Product of charge into distance. So the distance of separation is very less. So that's why the dipole moment of all these three is equal to that of that is D. That's why. So this is ABC is equal to D. Then finally both are equal strength but opposite direction operated. That's why both are cancelling each other. The net dipole moment is 0. Right. Next one. For example, take NH3 molecule or NF3 molecule. This is very important. Student is prepared for your examination. So the NH3 central atom is a nitrogen. It is bonded with 3 hydrogen atoms and have 1 lone pair of electrons. 1 lone pair, right? In NF3 central atom is nitrogen. It is bonded with 3 fluorine atoms and have 1 lone pair of electrons. Right. Now here, so compared to hydrogen, nitrogen is more electronegative. So because of this more electronegative, the bond electron cloud move more towards the nitrogen. That is the bond moment is towards nitrogen, and from hydrogen to nitrogen, also hydrogen to nitrogen, and the electrons are there. These are lone pairs of electrons. So dipole moment due to lone pairs of electrons is towards this direction because the electron cloud is there here. That's why. So all are in the same direction, right? So this is towards the nitrogen atom, and this is also towards because the lone pair is there for the nitrogen atom. So all are in the same direction. That's why if all are in the same direction, the net dipole moment is A, this is B, this is C, and this is D. The net dipole moment is A plus B plus C plus D. That's why you get maximum dipole moment for NH3. But what about NF3? So in case of NF3 here, compared to nitrogen, fluorine is more electronegative. That's why electron cloud moves more towards fluorine atom. That is the bond moment. The bond moves towards the fluorine. The bond moment is towards the fluorine. Here also towards the fluorine. Or here also towards the fluorine. Right? And here the bond moment due to lone pair is towards the nitrogen. Right? That's why here this is A, this is B, this is C, this is D. Then the resultant dipole moment MR, what is resultant dipole moment is so MR is equal to A plus B plus C minus D. Right? So this is opposite direction. So these are all towards the fluorine, and this is towards the nitrogen due to lone pairs of electrons. Both are in opposite direction. That's why the resultant dipole moment is equal to A plus B plus C minus D. That's why. So these values of the combining of this add up together, and you get this is D. Then the net dipole moment will get minimum value. Minimum. The resultant dipole moment is minimum. Why? Because the resultant dipole moments of 3 fluorine atoms is opposite to that of the dipole moment due to lone pairs of electrons. That's why the resultant dipole moment is minimum. Got it? Next one. The same manner, you can find out the dipole moment of H2O molecule. Here, the second atom is oxygen. It is bonding with two hydrogens and it have two lone pairs of electrons, right? Yeah. So here, compared to hydrogen, oxygen is more electronegative. That's why here the bond moment is towards the oxygen, and also towards the oxygen, right? Then here the dipole moment due to low pairs of electrons is also due to low pairs of electrons, right? Then all are in the same direction, right? This is also towards oxygen, this is also towards the oxygen. So that's why the resultant dipole moment is equal to this is A, B, C, D. There is A plus B plus C plus D. Then you get there is maximum dipole moment for water, right? So this is expected they find out the resultant dipole moment of water is 1.85 dBi units. 1.85 dBi units. You can convert it into coulomb meters. You get that is 6.71 into 10 power minus 30 coulomb meters, right? So this is, as you know, one dBi is equal to 3.335 10 power minus 30. Then 1.85 dBi you can get, you can multiply it. This and this will get it out. That is approximately 6.72 or 6.75 into 10 power minus 30 coulomb into meters, right? So this is about different covalent molecules have different dipole moment. We got it covered first. Next. Yeah, next one. What are the applications of dipole moment? Applications of dipole moment. What is the use? What is the significance of dipole moment? The concept of dipole moment. Once you know the dipole moment values of these covalent molecules, this concept is applied, is useful to know something. What that something is here? That is first one. It is useful to find ionic character. That is percentage of ionic character. Percentage of ionic character in a covalent molecule. As you know, in every ionic compound, some covalent character is there. Explained by Fawcett source. The same way, in every covalent molecule also, some ionic nature is there. Because as a polar covalent molecules, with the positive or negative poles, positive charges are there, negative charges are there. This behave like a ions. So that's why some ionic character is there in every covalent molecule, right? So how much ionic character is there in a given covalent molecule? How to know? That is known by using the formula. So that is the percentage of ionic character is equal to observed dipole moment value upon calculated dipole moment due to complete transfer of electrons. If electrons are completely transferred, then what happened? positive charge increases and negative charge increases, then automatically there is maybe more anionic character, anionic nature is more, right? So that's why here, what is observed dipole moment? It is calculated experimentally. It is experimentally calculated value, and this is theoretically calculated by applying the concept of that is complete transfer of electrons. So the value of these two will get a percentage of anionic character. Next, second one. This concept is useful to distinguish cis and trans geometrical isomers of organic compounds. Now, organic compounds exhibits geometrical isomerism, that is cis and trans isomerism. So, the same molecule, the same molecular formula, but different structural formula because of there is arrangement of atoms is different, right? So how can you distinguish it is a cis isomer, it is a trans isomer? How can you distinguish? This is based on the dipole moment values. How? That is, for example, I'll give an example to understand the concept. Then if there is an ethene, right? Ethene, right here. So two hydrogens are replaced with two fluorine, and here also two fluorine. So this is hydrogen, and here this is hydrogen. Now, so fluorine is present in first carbon and second carbon. This is 1,2 dichloroethene. 1,2 dichloroethene. And this is what these two are present in opposite atoms, but it is also two chlorines are there. One is the first carbon, other is the second carbon. It is also what 1,2 dichloroethene, right? Okay, so 1,2 dichloroethene, both are 1,2 dichloroethene. But here the thing is, the similar hydrogen atoms or chlorine atoms, the similar atoms are present on the same side. It is called cis 1,2 dichloroethane. And the similar atoms, hydrogens and chlorine, are present on the opposite side. This is called trans 1,2 dichloroethane. This is cis isomer. It is a trans isomer. Both are geometrical isomers, right? Now, so how can you separate it? How can you distinguish both of these? This trans, how can you do it? That is separated is here. Look here. So the dipole moment is carbon and chlorine bond. Carbon and chlorine bond. So compared to carbon, chlorine is more electronegative. That's right. The shared electron pair, electron cloud moves more towards the more electronegative chlorine. Right. The bond moves more towards more electronegative chlorine atom. And here also, so from carbon to chlorine, the bond moment is towards the chlorine atom, right? Okay, so this is the bond moment between these carbon and chlorine is some x value. The bond moment, that is the electron cloud moves more towards the chloride. The bond moment toward this one is some y. Then x is equal to y. How much amount of bond momentum is there between these two? The same amount is there here also, but both in opposite direction. This is towards this direction, towards this direction. That's why. So both are cancelled with each other. Then the net dipole moment is 0. But what about here? Both are in the same direction. The dipole moment is same direction. The resultant dipole moment is equal to sum of dipole moment. That is sum of bond moments of A and B. So it is considered as dipole moment of this is A, and this is the dipole moment is this is B. Then the bond moments of A and B will get the resultant dipole moments. So that's why here, so resultant dipole moment is equal to A plus B. You will get some value, right? It is not 0, right? You will get some value. That means if you find out the dipole moment values, if you are getting a 0 dipole moment, then you have to say this is a trans isomer. There is no 0, some value is there dipole moment, then you have to say this is a cis isomer. That means based on dipole moment values, you can distinguish the cis and the trans forms of geometrical isomers of organic compounds. This also there is the application of this. Next one. Dipole moment is also useful to distinguish ortho, meta, para isomers of aromatic organic compounds. So next application is it is useful to distinguish ortho, meta, and para isomers of aromatic organic compounds. You know, in benzene, if you take it, you can call as orientation effect. Benzene, right? So in benzene, this is the benzene ring. I'm taking here there is a chlorine, two chlorines. One is first carbon, other one is second carbon. 1,2 equation. This is called 1,2 dichlorobenzene or ortho dichlorobenzene. How many chlorines are there? 2. Dichloro. Then the equation 1,2. This is called ortho. So ortho dichlorobenzene. And another one I'm taking now. This is 1 and 3 equations. It is meta dichlorobenzene. And another I'm taking now. That is 1,4 dichlorobenzene. Right. Now, how can you distinguish these two? Not only dichlorobenzene, any ortho, meta, and para isomers. You can take ortho chloronitrobenzene, meta chloronitrobenzene. You can take the NO2 group, here chlorine, here NO2 group. So, meta nitrochlorobenzene, like that. Para nitrochlorobenzene, like that. So, any one example I'm giving now, right? Now here, so how can you separate this ortho, para, and meta isomers of aromatic compounds? Is here. See here, the dipole moment, that is the bond moves towards the chlorine atom because compared to carbon, chlorine is more electronegative. So because chlorine is more electronegative, the bond, the electron moves more towards the chlorine. It is the bond moment towards the chlorine, and here also the bond moment towards the chlorine. The dipole moment of this is some x value, and this is some y value. So both x and y are exactly equal. Exactly equal because here also chlorine and here also chlorine, right? So the dipole x and y are equal, but opposite direction. Please move toward this direction, move toward this direction, right? So both are exactly equal and operating in opposite direction. That's why both are cancelling each other. The net dipole moment is 0 because dipole moment is a vector quantity, right? Then here, so here this is the dipole towards this chlorine atom, and this is toward this one atom, and here this is toward this, and this is toward this. So mostly here both are in the same direction, right? Both are in the same direction, right? Both are in the same direction, except the molecule, right? So that's why if both are in the same direction, the dipole moment, the resultant dipole is for the A plus B. So this is a dipole moment of this one is this bond moment is A, and this bond moment is B. So then the resultant dipole is you have to add up together. You have to add up together. The sum of these two will get the resultant dipole moment. That is, it is maximum will get this maximum value get. And here, what about this? So it is moving this way, this is moving, but it's not exactly opposite direction, right? It's not exactly opposite direction. A little is there. That's right. That's why here. So this is A and B. The resultant dipole moment is equal to. You also add up to the sum to the but the value is somewhat less. Why? Because this depends on charge and distance of separation of the two poles. That's why here the value you are getting the minimum. Here the value you are getting is maximum. Then the order of dipole moment is always ortho isomer. The order of dipole moment of these three ortho, meta, para is ortho is maximum, next meta, next para is 0. That's why that means among the three, if the dipole moment of a molecule is 0, then you have to say there is a para isomer, there is a maximum, there is a ortho isomer, there is a minimum, there is a meta isomer, right? Okay, that means this is also one of the application of dipole moment. Got it? Got it? Yeah, next one. This is about the concept of dipole moment. Next one is bond parameters. Bond parameters. A covalent bond is formed, right? How it is formed? Either by overlapping of atomic orbitals according to valence bond theory, or by intermixing of atomic orbitals, according to hybridization, or linear combination of atomic orbitals according to molecular orbital, right? The covalent bond is formed according to valence bond theory, overlapping of atomic orbitals, right? Now, once covalent bond is formed, the overlapping of atomic orbital, the distance between the two covalent bonds is called bond distance. This is called bond length. And the average bond, the angle between the two orbitals which are get overlapped to form covalent bond is called bond angle. And the energy that is released during formation of one mole of covalent bond is called bond energy. These are the parameters which are used to know the strength of covalent bond and to calculate the nature of covalent bond, right? So that is the covalent bond is calculated, is measured by three parameters. These are one is called bond length, second one is bond angle, and third one is bond energy. It is also called bond dissociation energy, right? Now we are going to discuss each and every one in detailed explanation. Here, students, I will give extended tricks. You just follow it. Otherwise, you have to prepare all the different orders of day. It will not be stored in your mind. You're simply outrage. Then you feel bad. You're losing your marks. Then I'm giving here simple tricks, amazing tricks. You just follow this one. You can easily get it on site, right? So first one, bond length. So what is bond length? It is, for example, you take it atom A and atom B. So these two are combined. Then it forms a covalent bond, right? The average bond distance between the two covalently bonded atoms. Okay, between the two covalent bonded atoms. From where to where? From nucleus of atom A to nucleus of atom B. That is called bond length. That is the average bond distance between the nucleus of two covalently bonded atoms in a covalent molecule is called bond length, right? So then bond length is calculated by using this the radius of atom A, this is radius of atom B. Then if between these two atoms, there is no electronegativity difference. Electronegativity difference is zero. Which atoms? That is, for example, H2, N2, Cl2, Br2. These are all homoatomic molecules, right? The electronegativity of, for example, take the H2, one hydrogen is 2.1, other also 2.1, right? So there is no electronegativity difference in such molecules. Okay, in case of such molecules, the bond length is equal to radius of atom A plus radius of atom B. So in this formula we can calculate bond length of that homoatomic molecules. Then, if there is a electronegativity difference is not equal to 0, that is some value is there, electron difference. It is generally heteroatomic molecules. There is polar molecules, polar covalent bonds. Heteroatomic means what? Both are different atoms. Automatically, electron difference must be there, right? So in such case, there is, for example, HCl, HBr, or HI, or NH3, or H2O, etc. Okay, so now in this type of heteroatomic molecules, the bond length is calculated using formula, that is radius of atom A plus radius of atom B minus 0.09 into XA minus XB. So what is this? What is the RA, radius of atom A and radius of atom B? XA is electronegativity of atom A and XB is electronegativity of atom B. So by using this formula, we can calculate bond length of heteroatomic molecules. So these are non-polar molecules, these are polar molecules. Non-polar means which is found in the two similar atoms. Polar is not there. This is homoatomic. Polar means it is found in the two different heteroatomic molecules, right? Yeah. Next one. So many covalent molecules are there. So all the covalent molecules having same bond length? No. Bond length is different for different covalent molecules. Then how can you know how much bond length of this molecule, how much bond length of this molecule, how much bond length of this molecule? How can you know? This is decided by some factors. Now we're going to discuss about factors influencing the bond length. Here I'll give you an example. Factors influencing bond length. So bond length is influenced by, first one, bond length is inversely proportional to electronegativity of the central atom. This quickly just keep in our mind. Right. Keep, what is keep? Keep in our mind. Right. So I'll give an example, you can get the concept. For example, take HF, HCl, HBr, HI. Alright. So here, electron activity is more, bond length is less. So here, electron activity of fluid is more, and it is very less. So electron activity is less means bond length is more. HA is more, HBr, HCl, HHF. Right? HF is very least bond length. Next, second factor. So bond length is inversely proportional to number of bonds. This is also called as bond multiplicity. Bond multiplicity, inversely proportional. Multiplicity means there is the two atoms formation of multiple bonds. There is a double bond, triple bond. Presence of double bond, triple, more than one type of bond is called what? Multiple bond. One multiplicity. There is a number of bonds that are present with two atoms. There is also decided how. So, for example, here carbon carbon single bond, carbon carbon double bond, carbon carbon double bond. So this is in case of alkanes. This is in case of alkanes. This is in case of alkynes. Right. Here, so for example, like C2H6, look at C2H4, look at C2H2. This is ethane, ethyne. Okay. So how to arrange the bond length of this one? Here, with the two carbon atoms, single bond is present. Here, double bond is present. Here, triple bond is present. Number of bonds increases. Bond length is decreases. It is common sense. Only one person is there in the room. He will entirely move it, right? If only this much, two persons are there. Two persons are occupied. With the two persons, here one corner, here one corner. Bond length is one. If three persons are there, between the three persons, bond length is decreases. Four persons. Not a concept, not a subject, common sense, you know this one. This is the way how to prepare the subject, right? Then it's very easy, right? Okay, so there is a common sense. Why you're trying this is, you know, right? So that means as number of bonds increases, automatically bond length decreases. So that's why, so number of bonds is more, bond length is less. So they have to come closer. That's why here there is alkynes, bond length is very less, alkanes is more. Why? Because there only single bond is present. Okay, only single bond. Number of bonds is less. The number of bonds is 2. The number of bonds are 3. So bond length, that is bond number increases means what? Bond length decreases, right? So that's why here alkanes, there is ethane is more bond length. Next to ethene, next to ethyne. That is alkanes is more bond length. Next alkenes, next alkynes. As you know, we studied also, there is in alkanes the bond length is 1.54 angstroms. In alkanes it is 1.34 angstroms. It is on alkynes 1.20 angstroms. That is this. For example, this is ethane, ethene. Not only that one. Any alkane is given. Just follow this way. That's it. Copy it first. Both the sides. Yeah, next one. Here, next one is bond length is inversely proportional to number of, or the simple one, percentage of s orbital character. Percentage of s orbital character. Right. So, for example, for this, one more example I will give you. This is now this is one example. One more example I will give you. This is came for previous examination. The second example for that second factor, example 2. Because space is not there, so that's why I write now. Look here, for example, take it here. A carbon oxide single bond, carbon oxide double bond, carbon oxide double bond. Yeah. So for example, take it here, CO2 2 minus, carbon dioxide, here carbon dioxide, and here carbon monoxide. We lost again the increasing order of bond length, or which is having more bond length, right? Now here, in carbon dioxide, so carbon, here double bond, here two single bonds are there, right? And resonance structure also this one. And here carbon dioxide, so there is how many 2 pi bonds are present, right? And here carbon monoxide 3 pi bonds are present. So between the carbon oxide 1 pi bond, between carbon oxide 3 pi bonds. Here between the carbon here 2 pi bonds, let's all sigma bonds only one is there, right? That's why here what happened? The number of sigma bonds are over here. Okay, so this carbon oxide single bond, carbon oxide single bond. Here carbon oxide 1 pi bond is there, double bond is there, carbon oxide triple bond is there. So number of bonds increases, then bond length decreases. So it is more bond length, this less, this still less. So there is this is the order, right? Next, one more example regarding this one only. So example 3, this is also previous examination question. So they gave that is so carbon nitrogen single bond, carbon nitrogen double bond, carbon nitrogen triple bond. Right. So here I will do an example to understand this fine. Take it for example, CH3 NH2, that is a amine, that is methylamine. And here CH double bond NH2, this is called imine, imines, that is methylamine. And this is I'm giving CH3 CN, that is cyanides, these are called methyl cyanide, right? Now, so in case of here carbon hydrogen single bond is present, amines are NH2, right? And carbon oxide, carbon and double bond is called imines. And here it's carbon cyanide group, right? Now here single bond, here double bond, here triple bond is there, right? So as number of bonds increases, okay, automatically bond length decreases. Here single bond length is more amines, extra amines, extra cyanides. That's it. This is the way how to study, right? Next one. Yeah. Next one, this one, that is the third factor. For this, now I'm going to give an example. So that is bond length is inversely proportional to what? Percentage of s orbital character. Percentage of s orbital character. For this, now I'm going to do different examples. So they will make it confusion to you, but don't confuse it. I'll give you simple tricks here also. Look here, for example. Yeah. So here, double bond, triple bond. Here double bond, and here double bond, and here triple bond. That's it. They will do like this. They may not have hydrogens yet. They may not want hydrogens. If you prepare CH3, CH2, CH2, CH3, CH3, CH2, CH, CH3, CH3, CE, like that. If I'll write it, you can't do us. Okay, so this is the way how to prepare organic compounds. Hydrogens, the many valences are satisfied by hydrogens. To understand the concept, this is the way how to prepare, right? Now, so tell me, how many I gave this A, B, C, D, E, F. So, are in the order of maybe increasing bond length or decreasing bond length, and which one of them have highest bond length, which is the less bond length? How can you know? Answer this word right here. Percentage of s orbital character. So s orbital, you know. So here, so for example, first carbon, second carbon, third carbon, fourth carbon. So it is sp3 carbon, all are single bonds, all are single bond, no pi bond. It is sp3, sp3, sp3. So this is, so I'm mainly focusing about second and third carbon. I'm mainly focusing about, because to understand the concept, I need just only second the second and third carbon, what type of hybridization is there. That's I need. Okay. So now second carbon, the single bond, solar single bond, two carbons only single bond is there means sp3 carbon. So second carbon is sp3. Third carbon is also sp3. And here this is sp3, but second carbon, one pi bond is present. One pi bond is present means under boss sp2, sp2, sp2. This also this carbon one pi bond is there. This also under boss sp2, sp2. Right. Then come here. This sp3. What about this one? Two pi bonds are there. Two pi bonds are there means under boss. Second carbon goes sp. This also two pi bonds are there. Sp. Next come here. So this is sp2. This is also sp2 because this carbon also have pi bond sp2. Second carbon is sp2 and third carbon also sp2 and pi bond is there sp2. Right. Next one. Come here. This is this carbon one pi bond is there sp2. This carbon goes sp2 and this is three pi bond. Two pi bonds are there. Sp. This sp2. This is sp. Right. Sp. And here sp is also sp because two pi bonds sp, two pi bonds sp. Right. Yeah. Now the trick is, as you know, that is sp3, sp2, sp hybrid orbitals. So the percentage of s orbital characteristics. Totally how many orbitals are there? One s of 3 p orbitals. Totally 4 hybrid orbitals are there. So among that, what is the percentage of s orbital character? 1 by 4. 1 by 4. That is 25%. Remaining 75% is p orbital character, right? That is 25%. Then here, this is 1 by 3 s orbital. 2 by 3 p orbital. That is 33.3% s orbital character. Remaining 67 or something, that is p orbital character, right? Okay, 67.3. Next here, sp 1:1, right? That is 50%, 50%. So s orbital is 50%, right? Okay. So s orbital character increases, then bond length decreases. Over. Now, so what is the order here? What is the order here? The order is the order of bond length of all this is A or sp3 means personal s orbital character is very less. That's why bond length is more. So bond length is more A. Next sp2 B. Next sp3. What about this? Here two sp2 sp2 are there, right? Here bond is there, here also bond is there between the two. So that's why this is less. Next D. Next here what is there? One is sp2, one is sp. So that is increasing, right? Okay. So that's why what happened? So that is sp means s orbital increases. S orbital increases means bond length decreases. That's why next to E. Next to F. Both are sp. Got it? Comment first. Now, next one. Another one. Bond length is affected by resonance in organic molecules. It is affected by resonance. That means you have some influence in the bond length of organic molecules. How? So one example, take benzene. Benzene, right? 3 pi bonds are there. So between 1 and 2 carbon atoms, between these two carbon atoms, double bond is present. Double bond length, that is 1.34 angstroms. And between the 2 and 3, single bond is present. Single bond is present here, single bond. Okay. So that's the bond length between the 2 and 3 carbons is 1.54 angstroms. Generally, if you apply normal rule, that is normal general rules, here these two carbons have 1.34, these two carbons have 1.54. But practically in benzene, the bond length is 1.39 angstroms. So this is the experimentally finding bond value, bond length. Why? That means this bond length it is in between the single bond length and in between the double bond length, right? So this 1.39 is in between the double bond length and the single bond length, right? Why? Because these pi bond electrons are participating in continuous resonance, right? Because of resonance, here what is there here? Double bond is there. Here what is there? Single bond, no? If it is migrated. Yes or no? That's why all the carbon atoms, because of continuous migration of delocalization of shifting of pi bond electrons along the length of the carbon chain is called what resonance. Because of resonance, so all the carbon atoms high 1.39 angstroms. That is the bond length is affected by resonance. Yeah, next one. One more example will be here also. Take the carbon dioxide now. So carbon dioxide can represent like this, and also you can represent other resonance structures also. That is, you can represent like this also. So here how many are there here? So there is 1, 2, 3, 4, 5, 6. Because it is 1, 2, 3, 4. That is guess what? Positive charge? No. More number of electrons, formal charge. They gave a trick. This is negative. Formal charge, right? Okay. And here only what? Only one pair. This is a positive charge. Then you can represent this one. That means here is the first one, is the second and third. This is the 1, 2 negative charge. That is 2, 3 third oxide positive charge. Then you can represent like this also. Here triple bond and here single bond and here negative charge and here positive charge. These are the resonance structures of this. Okay. Okay. Now the bond length, because of this resonance, that means these are split here, because of this resonance effect, the bond length in carbon and oxygen atoms is 1.15 angstroms. But actually it is because of single bond, it is 1.24, because of this triple bond 1.10, but is in between these two 1.15 angstroms. So the carbon oxygen bond length is 1.15 angstroms is due to what? Due to resonance. Right? This is about bond length. Next one. Bond. Okay, my dear students, the time is over. They will stop the session. Next class will finish this bond energy and bond angle. Right? Okay. Yeah, up to that, your syllabus is also completed. You can prepare for coming Sunday examination. Fine. Now.